So we're going to start gas laws today. Now, gas laws are pretty short topic, but it's a really maths intensive topic. And you all know maths is where it's at, right? I don't apologize. I never apologize for loving maths. You shouldn't either if you do. All right, so the expansion of gas is not as simple as the expansion of solids and liquids. Now, solids and liquids, owing to their chemical bonding, they behave very predictably when they are heated, meaning when you take an object that is solid and you heat it up, it is going to expand. It expands in such a way it's mathematically predictable. We can mathematically predict how much big an object is going to get with any degree of temperature rise. Similarly, for liquid, the liquid will expand in a certain way, and they can also work that out. So the expansion and cooling of liquids and solids are very predictable. It's very easy to work out. It's very easy to understand and track. Gases, on the other hand, owing to the fact that we have one molecule here, and next molecule this side, and next one quite down at the bottom here, all right? The way they behave is going to be much different because number one, they're too far away from each other to influence each other, right? When we heat up these gas particles, they move faster, and when they move faster, they have different strengths. When we cool them down, they move slower, so it's going to behave and act differently. So this is why we have a whole topic covered or dedicated just to gas laws. Or just the gases, sorry. There are more factors to consider when dealing with a gas, mainly because it's a compressible substance. Compressible substance means that we can compress it. And by compressing it, we change the very nature of the behavior of our gas particles. So when studying the behavior of gases, three factors must be taken into consideration. And those three factors are volume, pressure, and temperature. Please note, sorry, y'all behave. All right, please note the units that we measure our quantities with. Volume must always be measured in meters cubed. So you all are going to have to do your conversions properly, right? Do them perfectly, perfectly, perfectly. Of course, I will go through it again with you all this time, but please make the effort to learn how to do your conversions because they're not hard questions, right? And the hardest part really for students is to figure out which equation to use and how to deal with them. And that's not that bad either. So we have volume must be measured in meters cubed. Sometimes you're going to get questions in centimeters cube. You all have to know how to convert cm cube to meters cube. Off the top of your head, anybody here can recall how to convert cm cube to meters cube? I'm going to give you a big hint. You have to divide by something. Anybody? Cm cube to meters cube. We divide by
10 to the minus 6.
Somebody's not hearing me? Okay. Jay, you hear me now? Yeah? No?
By 10 to the minus 6.
No. Well, actually, 10 to the minus 6 is the conversion number, right? When you want to convert from cm cube to meters cube, you divide by 1 by 10 to the 6. Or the flip side, you can multiply by 1 by 10 to the minus 6. These two things mean the same thing, right? If you remember how to do your indices, remember when you divide, your index becomes negative. So either one of them will work. You either divide by 1,000,000 or you multiply by 1 by 10 to the minus 6, which is 1,000,000th. All right, make sure that mic is not turning off again. So down there, good. Yeah. All right. So that is cm cubed to meters cubed. Folks, you better write this down. You better learn how to do this conversion, because I have seen questions where they give you marks just to convert cm cubed to meters cubed. That's giveaway marks. Please, 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 please write it down. Please learn it. All right, so next one we have is pascals. Sometimes you're going to get your atmosphere, your pressure in atmospheres as opposed to pascals. And we did do how to convert atmospheres to pascals. 1 atmosphere is how many pascals? Anybody want to see if they could jog their memory knowing that you have exams in a little over a month or 6 weeks? How many pascals in 1 atmosphere?
Plus one. Is it 1.01325 by 10 to the 5?
1.01 by 10 to the 5 pascals. This is what we've done in class. You please learn it. Please write it down, because when we're going to be doing questions on this topic, I am not going to be going through atmosphere conversion because we've done it before. Pretty please learn it. And then the last one we have.
10
You don't need to do it. That's really, really exact. But when you have to do conversions at this level, there's one. Oh, geez, I lost my pen. Hold on. When you have to convert atmospheres to pascals, the 1.01 by 10 to the 5 is fine. All right, that is good and fine as it is. All right, and then the last one we have, lost my pen again. Okay, last one we have here is Kelvin. Remember, we just did Kelvin. And to go from Celsius to Kelvin, all you have to do is add 273 to your number. That's all you have to do to go from Celsius to Kelvin, is to add your 273. So please note your conversions, folks. These questions will not work. They do not work generally if you use other units, especially the Kelvin part. If you use degrees Celsius, your questions are never going to work out because we're going to be multiplying by numbers. All right, so let's look at our 3 gas laws. We have 3 laws that we look at. We look at pressure law, Charles' law, Boyle's law, and then we combine them together to give us the combined gas equation. So here we are always looking at these 3 components in some form or fashion, always these 3: volume, pressure, temperature. So pressure law, let's read it very simply. The pressure of a fixed mass of gas is directly proportional to its absolute temperature, provided volume is kept constant. So what they say here, if you want to put it in plain English, pressure is directly proportional to temperature, all right? Directly proportional. And they said that the volume is kept constant. So how are pressure and temperature related to each other? Let's go down to simple mechanics, classical physics. How are pressure and temperature related? Temperature, you all know temperature is a measure of how much energy is in a system. All right, you all follow the little train of thought. So the higher you raise, the more you raise your temperature, the more energy you are going to have. Everybody okay so far, right? Let me just get a clean screen. All right, so when your temperature increases, the amount of energy in your molecules are also going to increase. What is one way, what are the 2 ways that we know how energy is found in a material? And you know, we have 2 forms of energy that we calculated. You all can remember? On a system, what are the 2 types of energy we know about? Starts with K and P.
Kinetic and potential.
Kinetic and potential. And in this case, kinetic, right? Kinetic energy will increase because your molecules now have more energy. When molecules have more energy, guess what? They're going to move faster. You all following the train of thought so far? That making sense? You can give me a thumbs up, or yes. All right, don't always have to answer. All right, so when our molecules are heated up, all right, the volume cannot change. So that means they're just going to get more energy. Your molecules are going to move faster. And guess what? When they move faster, they exert more force on each other. Let's think about it. Now, usually in class, if I would hear, I would get somebody to come and hit somebody, but or you could hit yourself. All right, let's just think about this. Pressure, we know pressure is force upon an area. If you just take your hand and slowly hit your next hand, you barely feel, you'll feel it hitting, but it wouldn't give you any kind of sting, or you wouldn't feel any big force. But suppose you take your hand and hit it really fast, ow, right? You will feel a larger force on your hand. If you all want to try it, you all can try it right now and realize that does happen. I have on my gloves, so it kind of not as hard as it should be. If you hit something very slowly with a little bit of energy, you get a little bit of force exerted on it. But if you take something really, really fast, ow, still hit in my hand, right? And hit it really, really fast, the pressure exerted on that object is going to be greater because velocity does increase your pressure. If you've tried it, please try it. You can hit the table really softly, very slowly with your hand and realize you don't exert much pressure on your hand. All right, but you hit it really, really fast with a great speed or great velocity, you have far more pressure exerted. So this is how we know that pressure and temperature are related to each other. When we heat up our gas, so let's put this in a nice sequence that you all could track or write on, because you're going to have to write it down at home. When you increase your temperature, when the temperature increases, the energy in your molecules are going to increase. And as a result, your molecules are going to move faster. And when your molecules move faster, they exert a greater pressure, not on each other, not only on each other, but on the sides of the container, because they're going to hit the sides of the container faster and harder, all right, which is a greater pressure. If you all want to remember, pressure is force over area. And when we have something moving very fast, we can work out the force, right? See how all our physics is going to come into play right now. Everything are going to start holding hands together and linking towards each other, right? So here we are talking about the same pressure that we did when we were talking about mechanics. Pressure is force over area. We can use a lot of common sense here. Plenty common sense. This is nothing but common sense here with some physics knowledge, right? See how our common sense gets more elevated as we get more educated. It's elevated. All right. So as your molecules move faster, they are going to exert a greater force on each other. And by exerting a greater force, your pressure is also going to rise in your gas. Now, this is meant for your volume to be constant. So what happens in a situation like this, we are talking about a container that is sealed, where the volume is not changing. It's a sealed canister. We usually talk about a sealed container or a sealed or steel, right, container, or something that's unable to expand. And what happens if you add heat to this gas that's in a sealed container, that gas is unable to expand. All right, because let's think about it. If you heat up gas, the molecules going to want to move away from each other. But in a sealed container, our molecules cannot move away from each other. So all they're going to just end up doing is moving faster and faster and faster, hitting not just each other, but hitting the sides of the container. So as the temperature increases, all right, so as your temperature increases, the pressure within your container is going to increase. And I'm pretty sure we've all heard about situations where when you heat up a canister, it will explode. There is that legitimate problem or fare with gas canisters. This is why they're tested in a certain way, those gas tanks that you get from NP, right? They're built in such a way that they can take some heat where they wouldn't expand to the point where they explode. Plus, they can explode. They usually explode by falling down, right, and not by heat. So that's why you can see those gas trucks passing up on the in the hot sun, and nothing's wrong with those gas canisters because they're built to handle that little extra bit of pressure when our gas is heated in the daylight sun. Right? But if you happen to break a container, then it's going to explode. And it's a tremendous big sound explosion. It will rock a building. All right? So everybody follow that little bit of logic? It made sense, or you want me to go through it again? You could hit yes or no, or thumbs up, or thumbs down, if you don't want to talk. All right, good. All right. So let's use this because I will ask you to explain how the kinetic theory of matter explains or accounts for our gas laws. And we can break this down. What I said just now goes straight with the kinetic theory of matter, which are everything is made up of molecules, and these molecules are always in motion. So I heat up my molecules gain energy, they move faster, and when they move faster, they exert a greater pressure on the sides of the container they are in. Voila, temperature and pressure are directly related to each other. And we have the flip side. If we go now and cool down our gas, all right, so now we cool down our gas, we are now going to have, let's use an XM pen for cool. All right, so suppose I cool down my gas. Guess what? My gas molecules now moving with less energy. And if they're moving with less energy, they're going to be moving slower. Just like how all of us move really slow in the morning when it's nice and cold. We all know that, right? We want to occupy the lowest energy state possible when it's nice and cold. Ain't nobody getting up fast out of their bed. We all know that. But when it's warm, we want to get out of bed quickly because it's just uncomfortable. Same thing works, sort of. When your temperature drops, the energy level drops. And when the energy level drops, your molecules are now moving slower. And because they're moving slower, they are exerting less pressure on the sides of your container. So you can see how pressure and temperature have a direct relationship when it comes to gases. And this only works when the volume is kept constant. So this is in a sealed container that is unable to expand. That is what we have happening in our pressure law. Now let's put this in terms of maths because everything needs maths, right? Physics is nothing without maths. If you have a problem with that, oh well. Let's see if I can get this to go up. One more, right? So since pressure and temperature are directly related to each other, we can divide by the T, and we're going to get pressure divided by temperature is a constant value. So for a given system, like for one question, if you have a certain scenario, the pressure and temperature will always be equal to the same value. Please note your pressure must be in pascals, your temperature must be in Kelvin for this to work. And if we were to plot a graph, since this is a nice P over T is a constant, this is a straight line relationship. So as the temperature increases, our pressure is going to increase. See how we get a nice exact graph here? As temperature increases, we know the pressure of our gas is going to increase. So it's a nice straight line graph passing through the origin. Now we can extend this to work with. So this is like, this is in Kelvin. This is actually in Celsius, right? So the graphs are the same thing. You have a nice straight line relationship between temperature and pressure. Oh, this came from somewhere else. Now, what is the experiment? How do we know to show this? What we have, simply, we have some air in a sealed flask. At the top of the flask here, we have like a rubber cork or a regular cork, and that prevents the air from expanding. The air is not going to expand any more than it is. So what we do, as we heat this up, our temperature is going to rise. And as the temperature of our water rises, the temperature in the gas is also going to rise. And what they do, they could go ahead and read the pressure and realize that the pressure is going to get larger and larger as my temperature increases. This is a simple setup. All they have is just a water bath. We all did use water baths. Water baths where we apply water, heat to a container with water to indirectly heat something. So we take the temperature of the water, because whatever the temperature of the water is going to transfer to your air. And as the air increases in temperature, the pressure of this air, of these air particles, are going to increase. So it's a really simple apparatus. If you all ever get the apparatus, I've put it into the handout. I think I have to check to see if I put that one up, but you all should know what the apparatus setups look like. All right, here we have a trapped set of air in a water bath. We heat up that water bath and we're able to read the pressure increase. So we're going on to Charles' law. Charles' law, let's go down further down. Charles' law, what it states, for a fixed mass of gas, the volume of a fixed mass of gas is directly proportional to its absolute temperature, provided pressure is constant. So what we have, suppose I have a container that's allowed to expand and I added heat to this container. All right, let's use a better flame. All right, since we do have Bunsen burners. All right, suppose I have a container and it's filled with gas and I apply heat to it where I'm heating up the gas. No, I'm not melting the container. So nobody come with that. All right, what's going to happen to my molecules as I heat up these molecules? Anybody want to make a guess? What's going to happen to these molecules as I heat them up?
They would gain kinetic energy.
They are going to gain kinetic energy. You're jumping right into the story. That's what we're talking about, right? So as our temperature increases, our molecules are now going to gain energy, and then they are going to move faster, right? Not only do they move faster, they also move away from each other, because the faster something moves, the further it can travel. Yeah, that makes sense, right? Right? If I roll something with a little bit of force, it's going to move a small distance. But if I really push and apply a lot of energy and a lot of velocity, it's going to move fast. You see how all our physics are coming together now to play. All right? So what happens, because our molecules have more energy, they are now able to move faster and further away from each other. And since this container is allowed to expand, our gas is now going to start expanding and moving further away from each other. So let's read and see what that says again. A fixed volume of gas, so that means the volume here, no, the volume of a fixed mass of gas is directly proportional to its absolute temperature. So as your temperature rises, your volume is also going to increase, right? Which is kind of common sense. We know this when things get warm, right? When we warm something up, it's going to expand, and when we cool it down, they contract. This is where we get this from. Charles is the one who looked at that, not just in, well, he looked specifically at gases, and he realized once we keep the pressure constant, right, and the mere fact that the gas is expanding, that means it's not going to have pressure building up. And by the gas expanding, the pressure is going to remain the same. Jan having problems to join. Right? So we see this, the easiest way to see this is in hot air balloons. All right? Anybody ever saw the videos of hot air balloons? They look like a lot of fun to go, right? And what happens when they launch a hot air balloon, we know if we, let's get a, I don't have to draw it, I can find a good image on it, right? So what happens with air balloons, they don't launch it with full size at ground level. Why? Because it's going to expand as it gets higher. We're going to explain this when we do all the gas laws together. All right, but hot air balloons are how one of the good reasons or good examples of as you raise the temperature of a gas, it will expand more and more. All right, so if you want, you all can go and look it up. All right, there's tons of experiments, tons of stuff that happen with how air balloons work. They talk about buoyancy, they talk about floating and sinking. Remember, we did that with Archimedes' principle. They talk about how gas behaves when we have greater temperatures. All right, so there's a lot of physics in how balloons work, or especially hot air balloons work. All right, I'll look to see if I can find a good diagram on it for you all. All right, but what they do, they don't launch hot air balloons at full size at ground level. What happens, because as it heats up, it's going to get wider and wider, or the balloon increases in size, so you are able to float up. I'm not seeing anything here on size differences, but I'll send it to you afterwards. I'm seeing memes. Why am I seeing memes? You all, memes rule the world now, you know. Anyway, so here we can also see that both of these are also directly related to each other. Volume is directly proportional to the temperature, because as the temperature rises, your volume is also going to increase. And flip side, as the temperature decreases, your volume is also going to decrease. Now, there's the next way of looking at this. This is how we are able to look at gases being liquefied, because when we take a gas and we squeeze that gas, the volume is now going to decrease. And by squeezing that gas together, we are inadvertently causing the temperature of the gas to decrease also, right? Why are they decreasing? Because the gas molecules have less place to move. They have less energy because the pressure is remaining constant. So they're now going to start slowing down because they've slowed up how much they have to move about. And so as your volume decreases, your temperature is also going to decrease. So that's why when we have liquefied gases, they have to be at very cold temperatures. If you all want, just for academic curiosity, and I do encourage your academic curiosity, go and look at what temperature hydrogen, helium, oxygen, and nitrogen exist at room to be liquid gas, right? What temperature do they liquefy at? Right? It's really cold temperatures. I think hydrogen turns into liquid around minus 260 or 250 or something like that. Go and look it up. What temperature it takes to liquefy these gases, or the boiling point of these liquids. Right? You're going to see how cool they have to get in order to liquefy them. So our equation here is V over T is equal to a constant. And when we have a given situation or a given system, V over T is going to always be a constant value. So we can talk about initial values being equal to final values when we divide them. When we start doing questions, you're going to see how this works out. So when we're talking about the graph setup, if you look at it from the Kelvin point of view, all right, or the Celsius point of view, all right, this is using Celsius here on the scale. There's a point when your volume can be the smallest it can possibly be, and that's at 0 Kelvin. At 0 Kelvin, an object can shrink no more. It can get no smaller than it is at 0 Kelvin, because our molecules are now combined together. They have no more energy, so they can't move anymore. They can't get any smaller. They can't move anymore together, right? So that is what we talk about when something reaches 0 Kelvin. Not only do they lose all energy, all your molecules stop moving, and it can't get any smaller than it already is at that temperature. All right, so that's the coldest anything can get. All right, and I think at 0 Kelvin, right, everything turns, all liquids turn to solids. Everything freezes at 0 Kelvin and whatnot. So you get a nice straight line graph if you wanted to go from, if you want your temperature in Kelvin and you want your volume. Why is that in kilopascals? Hello? That's supposed to in meters cube, right? It won't reach to 0. all right? Because something can't always get small, but you have a nice graph here where your temperature um, crosses at a certain point where your temperature reaches 0. So it's a nice straight line equation, really easy to work out, really easy to read your values, all right, and whatnot. The apparatus to set up, the way how the apparatus is set up to read this is really simple apparatus. If we had gas this year, I would have run it with you all, but wasn't enough time to set this up. But guess what? Next year is lower 6. Those of you all who are going to meet with me lower 6, we're going to do this. Well, yeah, we're going to do this because we will have gas and I'm going to make it run. So it's a next simple thing. We have a water bath. You know, water baths are the best way to heat things without just heating up one spot. So we have a water bath here. What they have a little ruler, and we take a capillary tube, a fine capillary tube, stick it onto the ruler. We trap some air by just putting a little drop of concentrated sulfuric acid, because you all probably haven't seen concentrated acids that we have in school, but you'll see them in Form 6. The concentrated acids are basically like syrups. They're thick liquids and not as fine, watery, runny liquids. All right, concentrated acids are really, really thick, especially sulfuric acid. All right, it's probably as thick as honey or corn syrup. I corn syrup. So you can just take a drop and put it in the capillary tube, and it's going to stay there suspended in the tube. And what it does, it ends up trapping the air. You see this little bit of air inside here? It traps the air. So the air is not going to escape through the acid, right? Because it acts as a plug. But because acid is a liquid, it's easily going to move up and down that tube. So what happens as we apply more heat to our water bath, the molecules in here are going to want to expand. They're going to want to stretch out and go different places. And because this little this little drop of sulfuric acid is a liquid, it's easy to move up and down the tube. So as the gas starts to expand, this little bit of sulfuric acid is just going to move up, right? It's just going to move up the capillary tube, and now you're going to see where the gas is actually, or how much gas is actually expanding in your tube. So all you have to do is to read the difference in heights, and we can work out how the volume has changed with pressure. How would we do that? All right. If we can read the temperature of the water bath, it's not going to get over 100 degrees Celsius, so it's not a very dangerous experiment, you know, to say you're going to get horrible burns. It's a little small beaker where you're supposed to be nice and careful with. And you all were really careful in our beaker lab or our test tube lab. So, and what you do here, since a capillary tube is essentially a long cylinder, and you know the length of it, right? And a cylinder, you could go and read the cross-sectional area. We can take vernier caliper and read the cross-sectional area. You can read the diameter, we can read the radius and work out our volume. So it's not a hard lab to do. We're going to do this for sure. Those of you all who will be with me next year, well, come September, October for lower 6. All right, so we're going to try to do this, but really simple apparatus. And you can see here, as this water cools down, the gas here is going to contract, and the little bit of acid is going to fall back down. All right, so as our gas expands, it's going to push the acid up, and we are able to measure, really pretty accurately measure how much the volume changed. So the simple apparatus too. All right, hope we can do it next year. Then we have last one, Boyle's law. Boyle's law is the one that people get a little mixed up with. All right, sometimes Boyle's law. So let's read. Oops, wrong marker. Boyle's law. The pressure of a fixed mass of gas, so we're looking at pressure, is inversely proportional to its volume, provided the temperature of the gas is kept constant. So what they're saying here, they're saying that pressure is inversely related to the volume. Inversely means as one goes up, the other one is going to go down. That's what we talk about, an inverse relationship. Anytime we have an inverse relationship, right, that means as one changes, the other one is going to change in an opposite manner and fashion. So here, as pressure increases, volume goes down, and as pressure decreases, volume is going to go up. Let's see how that works. Let's use some common sense knowledge to rationalize this out. So I have a container, right? This container is somewhat flexible, right? The temperature of the gas remains constant, so we're not looking at how temperature changes. Now, if I were to squeeze this container, this is real common sense, folks. Some of these are common sense. If I applied pressure on all sides of this flexible container, wouldn't it get smaller if it's filled with a gas?
Yeah.
Common sense, real common sense things, right? If I squeeze it down, so that means the volume is going to get smaller, right? When something gets smaller, the volume decreases. And likewise, if I were to release the pressure I'm putting on this, it's now going to be able to expand and get larger. Whoops, sorry. Who is messaging me? Oh, I will see just now. So we can see here, as pressure increases, volume decreases. Why? Because when pressure increases, we are literally squeezing the gas. Yes, okay, I'm seeing who's calling me. Right? So here, this is where we get an inverse relationship, and inverse relationships are illustrated by the use of a curve. But we've done half-life already, so we kind of know what this curve is going to look like. I think I've lost my pen. All right, so let's look at this. All right, say I have a gas. I have a gas at its maximum pressure. All right, and now I decrease that gas. So I have my first pressure here. I decrease that gas, right? The volume is, I'm looking at the wrong way. Suppose I have a gas, right? And my pressure is some pressure, pressure 1. It's going to have a particular volume, right? And now I increase the pressure of that gas. So I'm now increasing my pressure of my gas. Because it's contracting, the volume of that gas is going to get smaller. If I increase my pressure again, I have now squeezed my gas even more. And by squeezing the gas even more, I've reduced the pressure to even a smaller value. So that's how we end up getting a curve to show your relationship. Now, mathematically, we can't do much with a curve other than taking values, but there is a way to convert this curve into a straight line. So when we have P is directly proportional to 1 over V, this is how we get an inverse graph. If we plot a graph of P and 1 over V, so we plot a graph of P and 1 over V, we are going to get a straight line graph. I'm going to give you a question where you're going to try it and plot it yourself. If you don't want to plot it, that's your loss, because every bit of practice and knowledge right now for you all is going to be to your advantage. All right, I want to finish up here. All right, I have the apparatus labeled up here for you all to try and see how this works. So common sense, when you increase the pressure, your volume is going to decrease, and vice versa. When your volume increases, you've released pressure. Right? Why have you released the pressure? Your pressure has decreased because our molecules are now no longer contracted, hitting into each other. They're moving away from each other, so we have less force from the molecules on each other, less velocity of the molecules on each other, so your pressure decreases. So it's a really easy relationship using common sense. That's why I tell you at CSEC level, we still live in the world of common sense. So again, expanded common sense. So we do have our basic physics knowledge now, and we can expand it. So when we want to get a straight line graph, we plot a graph of pressure versus 1 over volume. All right, I'm going to send you the note on how to look at it maths-wise and gradient-wise, because again, all our straight lines y is equal to mx plus c. There's an easy way to see how this works out. So I'm going to send you it and show you it just in case. So I want us to wrap up there because I want to speak about the exam topics. All right, I do have the exam topics for you. Actually, I can just insert it. All right, so let's put it in quick. Exam topics. All right, so they did release the document with our exam topics for this year. We're going to speak about this more in depth. Now, it looks like a lot of questions, a lot of topics that they're covering for our 5 questions. But if we look at this, folks, let's learn to break down what they've sent us. All right, if you all didn't put it, I'm going to put it back up. These are the exam topics. I think that they're going to put graph work, deformation, and turning forces, all right, as our first question. All right, so that's going to be our question 1. Deformation here is Hooke's law. All right, deformation here is going to be using moments and whatnot. Then we have our next question. We have, let me just put it in colors. Now we're going to think about this more in depth. Temperature and gas laws. That's our question 2. Or one of the questions. It's going to be talking about temperature scales, and it's going to be gas laws, which we've done today, and we have more questions to do. Then we're going to have a waves and light question, and look at the amount of topics here. Types of waves, speed of sound, reflection, refraction, critical angle, and total internal reflection. So that means it's going to be a whole bunch of small little parts. Like they're going to ask you what type of wave this is. They're going to ask you what is the speed of sound. So if you want to bet, they're going to ask you to identify what type of wave sound is. Right? But that's the next question there if you want to use some logic and how they've put out these topics for us. Then we're going to look at alternating current and resistance. That could be one question by itself. All right? Why I'm saying that is one question by itself, because magnetic forces, electromagnetic force, and motors is one topic. That's electromagnetism. All right, so we're going to go through that, see electromagnetism. And then our last question is going to be particles of the atom. They're going to ask you to label a diagram of the atom. They're going to give you an isotope and tell you to identify which these 3 particles are and how many of them there are. We've done those questions. They're going to talk about radioactive emissions, alpha, beta, gamma. We're going to go through everything on them. So when we're going to do revision, we're going to cover one revision section on each topic as much as we can. And then half-life. They're probably going to give you a graph to go and read off half-life. All right, or tell you how to work out how many half-lives of something. So that's our questions for this year exams. That is the breakdown that they've sent us. I know I'm going a little bit beyond the class, but I'll just finish this up. All right, and we're going to see what we get. So we should be finished with the syllabus in a week and a half. All right, since I am home on quarantine and they've canceled moderations because of the COVID numbers. It's ironic that my quarantine takes place while the moderations have been postponed. It's almost, wow, a little too coincidental. All right, so I will be back here with you all. I know I will be recording the session on heat transfer because that's not it's not a calculation-based topic, so I can basically just call it out for you all. Again, I will invite you. I will tell you when I'm doing that recording. It will be sometime tomorrow or Friday because I only have single periods that day. All right, so if you all are free and you want to stop in so you can ask some live questions, you can do so. But I'll literally ask questions. I'll be kind of lonely back here just talking to myself. All right, so that's it. So we should be finished with the syllabus in a week and a half. The next day, we will go through the gas laws, how to do the calculation, and you're going to get a tutorial in it one time. All right, so look out for the tutorial. It's coming. And we're going to start doing work one on each topic. Please note, these are only your paper 2 topics. The paper 1 topics still cover as much of the syllabus as possible. Can't really say how much of the syllabus it's going to cover because you can see a lot of things have been left out. They've left out the entire of mechanics. No pressure, no velocity, no Newton laws, no hydrostatics. A lot of mechanics has been left out in this topic, but that doesn't mean it's not going to be in the other one. Same thing for temperature. I only see temperature and gas logs. They have not spoken about heat energies, which we will do. They have not spoken about heat transfer, which we will do. All right, and whatnot. They've look like they've covered light and optics really well, so that's going to be okay. Alternating current and resistance, we've done those, so it's just going to probably be a circuit question. That could probably be a circuit question. Magnetic forces, electromagnetic force and motors, we're just going to revise our two motors and do that. If you notice, there's no electronics in this. No electronics, so logic gates and all those things, smoothing and rectification and stuff will probably be, you still will have to study it for multiple choice. And likewise for, well, the atomic physics part, they've covered it pretty well. What they don't have in there is like the evolution of the atomic model, isotopes, and safety precautions, but it could be in there too, right? Because I don't trust CXC to just give us the exact topics. They could still come and hit us a curveball. But those are our topics. I'm going to post it up. I think you all should have gotten that document from numerous places by now. But I'm going to post this up, and it's going to help us guide us for our paper 2 review. All right, so we'll stop the recording there. Now we'll get out to the share screen there. All right, let's put this in here. All right, so next day, which is next week. I don't see you again this week, I think. No, I see you on Friday, right? Or not? No, I don't see you on Friday. All right, whichever day. We will finish it up. As I said, we'll do the recording. We're going to get this done within a week and a half, and we'll finish with the syllabus. And then it's questions and questions and questions. All right? So, folks.
Tuesday.
Thursday is a holiday.
Really?
Thursday is a holiday. So, since I won't be seeing you before Thursday, right? Eid Mubarak to any Muslim students that I have. Have a good day. It's going to be a quiet Eid, just like we had quiet Diwali. Not so quiet Christmas. You all know what happened in Easter. All right, but enjoy your Eid. Have a good Eid. I already bought, even before I went into lockdown, I have my sawine ready to make. All right, so you all have a good week. Have Eid Mubarak to my Muslim students or families or whatnot. All right, you all be safe, continue being safe, and I will see you later. Bye-bye.
Bye.